Hello everyone, how's it going? So, hope you feel caffeinated enough after this coffee break. So before going on with the presentation, I want first to thank the organizer of this awesome conference. And it's a pleasure for me from being here again, even this year. And let's give a round of applause for the organizer. So, hello everyone, my name is Mattia MANZATI. I am a core contributor of Effect. I work mostly on the dev tools, and I'm a founding engineer at Effectful Technologies. And, well, today I want to talk about something that's actually not brand new or shiny. And yes, as the title has spoiled, today we're talking about JavaScript generators. And we know that they are something that has been in the language for almost a decade, but yet I believe that is still a completely underrated and forgotten feature of the language. So today we want to go to change that, because we'll explore what makes generators magical and see how they can solve real-world problems in a very elegant way. So first thing, what is a generator? Well, a generator is a special kind of an iterator, and that's it. So what is an iterator? Well, an iterator defines how to iterate over something. And to simply put, is basically just an object with a next method on it. And when you call next, you are supposed to return a structure with two properties, a value and a DON. And value contains basically the value that your iterator has just produced, and done is a Boolean that basically tells if the iterator is done iterating or not. And so now you may be wondering, how do you create generators? Well, we use generator functions. Yeah, I know that the naming can be a little confusing, so let's be clear about the terminology in here. We have generator functions, and those are the constructors for generators. And then we have generators, also called generator objects or generator iterators, and those are the actual object instances with the next method that we have described before. So basically, a generator function is kind of like a factory, and calling it produces a generator iterator. And this distinction is very important to keep in mind during our presentation. So, generator functions have a special but yet very familiar syntax to what we are used to, because they are declared by using the function star keyword. Notice the star we have after function. And inside, they may use some yield instruction to produce values. And the first thing that I always get asked, can I use generator arrow functions? Unfortunately, not yet. There is a stage 1 TC39 proposal for arrow generators, but it's not something that we see coming in the foreseeable future, unfortunately. So let's see a real generator function in action. So this generator function basically yields 3 strings. And when we call the generator function 123go, what happens is that we don't get back the return value of the function, but instead we get back a generator iterator object. And then we can call, again, the next method over that generator iterator object. And that will basically execute our generator function until it hits a yield instruction. And when it hits a yield instruction, it will pause and then return that object that we have described before with value 1 and done false, because we are not done iterating. And when we call it again, we will get value 2 and done false, yet until we reach the end of the body of the generator function. And then we will receive done true, because we have finished it, and the value will be the return of our generator function. But here's where the magic shines. What happens if you have local state? Well, we have here, for example, a count variable that is created inside of our generator function, and then we yield. And when we yield, what happens is that the function pauses completely, and the local state is preserved. So when we call next again, the magical thing is that the scope is still there, the variables are still there, and the execution basically resumes where we left off, with all of our local variables intact. And we can also see that this is a very special ability of generators of basically posing the function, yielding back the control of the JavaScript loop to the caller, then the caller can do whatever it wants, and when the caller have the ability to call next again, to give back the control of the execution loop to the generator function. And this ability of yielding back control is indeed what I think one of the superpowers of generators that we will explore today. But again, generators are not just generators, they are also iterables. So what's the difference? Well, an iterables is basically an object that has a symbol.iterator property method that returns an iterator. But I don't want to care too much about how they are implemented. The thing that I want to focus is that generators have built-in iterable support. So that means that they work seamlessly with all of JavaScript iterator features. So you can use generators in for-of loops, or with the spread operators, or with array.from, and any other API that respects an iterable. So this makes generators something that feels completely natural as part of the language, not something that has been bolted on lately. And another instruction that you may encounter inside of your generators is the yield star instruction. And what is it? Well, yield star is a special variant of yielding that basically yields all of the elements of the iterable that has been provided. So we have here basically the same code. We are changing the code only by one character. On the top, we have a regular yield. On the bottom, we have a yield star. And we can see that the output is indeed different, because in the first one, we are just yielding the array, and that's it. And so it produces only one value, the array. And on the second one, instead, we are yield star the array. And the array is iterable, so it will yield all of the elements of the array, one after the other. And here's where yield star really shines, because you can create basically generator composition. Because since, again, generators are iterables, that means that you can yield star an invocation of another generator function. In this example, we have a main function that basically yields 2 times the 1, 2, 3 twice. And the beauty is that for the consumer, this is just a flat sequence. It just sees 1, 2, 3, 1, 2, 3s. So that means that it doesn't care about the internal composition. You can basically have infinite composition, build your very basic building blocks, and compose them to build very, very complex generator functions. And another very interesting power of generators is lazy evaluation. Because look at this code, we have a while true loop, and normally this would freeze your program and starve your thread. But with generator doing this is perfectly safe. Why? Well, because yield poses the execution and pass back control of the execution to the caller. So that means that the loop will run up until it yields, and then it's up to the caller again, call next, in order to resume the execution. So that means that we have code that basically executes on demand, not eagerly. So you can see that, for example, this generator will keep producing values forever. We can call next 1,000,000 times, and we will get value forever. So that brings us to an important concept, that basically generators are pool-based data structure. So what does it mean? Well, it means that they can generate values on the fly when next is called. So this is perfect for things when you have, for example, in-memory computation that are very CPU heavy. Maybe instead of performing all of the batch of the work in a single shot, you can use generator to break that loop and produce values as they are requested. And that opens up things like, what if we use generators to describe, for example, animations? Because again, we have API for, say, hooking up callbacks and say, OK, I want a new frame. So with request animation frame, we can ask the browser, call this function when we want a new frame. And it is amazing because we can hook that callback to basically just invoking the next on the iterator and produce the next state for the animation. And then we can update our DOM accordingly. But this is awesome, but the really interesting and amazing part is that generators can receive values too. So the yield expression doesn't just produce value, but it can also receive back once. So when you call next with an argument, basically the argument that you provide becomes the value of the yield expression inside of the generator. So in this example, our generator asks question and uses the yield instruction to wait for answers. And then by passing the values in with the next, we basically provide back the value to the generator. And some companies don't want to tell you, but basically this is how any AI is implemented. It's basically a generator that yields something and waits back for a reply. And that number that they usually speak about, the number of million of context token, is basically the amount of if statement that they have inside the body of the generator. But yeah, jokes aside, you may think, oh, well, I've never used the generator, so why should I care about that? Well, the thing is that you have already used something that is really similar to generators, and you just don't know it. Because every time you use something like an async await function, basically you are probably using a generator under the hood. Because look at those two functions. They are almost identical, I would say. The async await syntax was introduced, I think, in ES 2017, while we had generators since ES 2015. So clever people working on Babel and other transpile realized that maybe we can convert async await back into generators. And then we can have basically a generator that yields promises. And yeah, this is useful, but again, we want a promise. We don't want a generator that yields promises. So what they did is they basically had some kind of generator runner that basically took that generator iterator that was yielding promises, and whenever the generator yielded the promises, it will basically chain back with then the invocation of the next step. So basically, they built a step chain where the value from the previous promise that got resolved will be injected back into the previous step of the generator. And this is a bidirectional flow that yields promises and gets back the resolved value. And again, this made async await work when support wasn't there. And this pattern of request response is really nice, but can we have also other responses, other patterns? Yes, we can have other patterns. We can, for example, implement the actor model by using generators. And what is the actor model? Well, for those of you who doesn't know, the actor model is a pattern that was invented by David Cruci. No, sorry, it was invented in 1970. And the key idea behind that is that you basically, instead of having a shared memory in your application using logs and multi-threading and whatever, what you can have is 1,000 of actors, and each actor has a private state and a mailbox for receiving messages. And the actor will communicate by exchanging messages. And no shared memory means no race condition, no deadlocks, and whatever. And the beautiful part is that generators are a perfect fit for implementing actors, because they can maintain private state, they can yield for wait messages, and they can process one at a time. So let's see how we can implement that with generators. So first we need to build some infrastructure. We basically need to create an actor system which will keep track of all of the actors in our system by using, for example, a record, an in-memory record. We will have two functions. We will have the spawn function, which will basically allocate new actors inside of the actor system by creating the generator iterator and starting the first invocation. And secondly, we will have a send method. And the send method will basically take in name of the recipient plus a message. And by looking at the name of the recipient and the memory, it will route the message to the correct recipient and call the next on the correct recipient. So showing that in action, we can see that we can, for example, have the classic example of two ping-pong actors that they are sending each other messages. And you can see that here we are still leveraging that while true pattern in order to have the actor always alive. And the first thing that the actor does is step up and wait for messages. And when the message comes, it processes, it does its thing, and then it uses system.send to basically interact with other actors in the system. So this is a really simple pattern, but can be used for more complex things, like you can have a chat room actor, and the chat room actor, for example, can keep a private state, which is the list of connected user, and can receive messages from actors like, I want to join, and then it will record the name of the actor and send a welcome message. Then you can receive messages and broadcast them to all known participants. And also, when a leave message arrives, it will basically remove the actor from the list of participants in the chat room. So this pattern can really scale to production system. So we have seen that generators enable these beautiful patterns. We have seen that they have lazy evaluation that allows to create infinite sequences. We have seen how even async await was baked by generators. So generators are not some toys, they are something really powerful. But what we are missing before going to production? Well, we are missing type safety. So how do we make our generator fully type safe? Well, turns out that TypeScript already has a great support for iterators. So TypeScript is already able to describe what an iterator is. And basically, it can describe it with an iterator that has 3 type parameters. We have T, which is basically the type that generator yields. And we have tReturn, which is the type of the return of our generator iterator. And we have tNext, which is basically the type that we expect to pass in when we call next over our iterator. And how do we use that with generator function? Well, we can use the generator type to just annotate the result type of our generator function, because again, the generator function won't be executed, but it will only return a generator iterator. And it accepts the same 3 type parameters. So in this example, we can see that we yield number, we return a string, and we accept a Boolean. And then indeed, TypeScript will force that all the typings are correct. But turns out that TypeScript already provides good inference even for very basic generators. Because here we have, for example, a number generator that yields 1, 2, and returns true. And turns out that TypeScript is able to automatically infer that that is a generator that yields number, returns a Boolean. And unfortunately, it cannot know what it gets inputted. But that also means that TypeScript can also leverage the control flow analysis to basically narrow the type based on if the generator iterator is done or not. And we can see that indeed it sees that value is a number, because if it's not done, it means that the generator is yielding values. So the type we are yielding are numbers and not Booleans. But here's something cool about the yield star that we mentioned before. Well, yield star evaluates it's to the return value of the delegated generator. Okay, these are hard words, but let me break it with an example. So when we yield star inner, what will happen, it will yield all of the values of the inner function generator. So it will yield hello, it will yield word, and then it will return the number 42. And we can see that indeed TypeScript is smart enough to get the inference of the result to be a number. So that got me thinking. I don't love manual type annotations, but unfortunately I cannot put type annotation over the single yield statement. But I would really like to do that. I would really like to put the types on the yield statement and get automatic inference for the whole generator. But seems like TypeScript doesn't support that out of the box. But let me show a pattern that can maybe change everything. This is the OP pattern, also called single shot gen. And this is basically a generator iterator that yields the value which this class has been constructed with once. And once it has yielded that value, it will return as return value whatever you passed into next. So basically, the first time it will yield hello in this case, and the subsequent time it will return done true, and with value whatever you pass into next. So you say, okay, why should I care about this really weird code? Well, the magic happens when we use that with yield star. Because now, instead of yielding strings directly, we can yield new OP instances. And we can put local type annotation on the OP object. And The magic part is that TypeScript is able now to infer the return type for name and age variables. And so that means that you can fully leverage inference for the full generator type. We just typed the instruction, and now it generated all of that. So again, why should I care about that? Well, if you think about it, those OP patterns really remind me about building a custom DSL. So basically, that means that we can build our own custom DSL for our application by using typed instruction classes. Yeah, sure, I'm using classes, but we'll see that's not mandatory. And so we can say, for example, that those are the very basic building blocks for our DSL. We have a prompt string instruction, we have a prompt confirm and an alert, and we see that they are typed because every instruction, for example, from prompt string says that it expects back an OP that returns a string. So we will yield an OP prompt instruction and wait for a string back. And the same goes for confirm, that will basically yield a confirm instruction, but expect a Boolean back. And the alert won't expect nothing back. And now that we have those beautiful instructions, we can use them to build our own DSL, for example, for an onboarding flow. And this is amazing because this is entirely our behavior description, and it does not implement in any way logic of how those instructions are actually implemented. It is just a DSL. And then we can, again, like async await was transpiled back in the time, we can then build our own interpreters for the instruction yielded by our generators. We can, for example, use the readline module from Node, for example, to read the input from the terminal, and use console.log for alerts. And again, we can also swap this interpreter for another one and keep the same generator as before with the same business logic. So that means that we can have, for example, something that we hate doing, but a test interpreter. We can basically create a test interpreter that just uses predefined responses, logs all of the instruction, and then asserts that the yielded instruction by the generator are exactly what we expect, and the responses will be used like a mocked responses. So this is ultimate testability because we can have tests that basically run the generator without using the actual real-world implementation. And then we can have separate tests that only assures that the implementation of the single instruction is correct. And by then, if one is correct and the other is correct, the composition of those should be correct as well. And again, generators being pool-based and lazy gets you another benefit because they automatically solve the function coloring problem. And for those of you who doesn't know, the function coloring problem is basically, let's say that you have synchronous and asynchronous functions in your code base. You start in your code base by having a function, something like readConfig, that is synchronous and just uses value from a process.m variable. And now you have functions all over of your code base that are synchronous as well because, again, it is synchronous, so you can have synchronous function. But then some change of requirement happens, and then now you need to retrieve the value from a database. So that means that you have to change all of the function that invoked that readConfig function into async ones. And that usually isn't so great to do. So usually what people end up doing is basically saying everything is async, which again is not good. But with generators, again, we don't care because it's the consuming interpreter that decides if the instruction is synchronous or asynchronous. From the business logic implementation of the generator function, we don't care. We just yield an instruction and wait for the response. Will it come synchronously? Fine. Will it come asynchronously? Fine as well. And again, as I mentioned before, that new constructor that I've been using is not a requirement of the pattern. It's something that I used as implementation detail just because I love to have those basically opaque type names in our type system. And speaking of types, I've just noticed that the inference of the generator basically inferred that inside of our generator function, we are using both the prompt string and the prompt confirm. So basically, the TypeScript inference is inferring exactly the instructions that are yielded inside of our generators. So what happens if we have instructions that have generic type parameters? Well, it turns out that inference here works as well. So we infer locally the value of the key for the redenv instruction, and then when the whole generator gets inferred, it will infer automatically the generator with our typed redenv instruction. And this works not only for a single instruction, but you can have as many instructions as you want inside of your generator, and that will still work. So that got me thinking, what if we can do some type level extraction to extract those generic type parameters that our instruction have in order to provide, for example, type-safe interpreter? Because again, if we had a redenv instruction, we expect that somehow we provided that env, right? So we can, for example, extract all the env key that are read by the redenv instruction and then ensure that they are actually provided where we call run to actually run our generator. So we have seen that this pattern is so powerful because you get fully type safety without manually annotating the generator's type and inference flow from your instruction. You have a completely separation of concern because, again, generators contain just the business logic. They don't care about how instructions are implemented. And that means that they are fully testable because you can just mock the interpreters. But fourth, generators can also compose beautifully by using yield star. And also, they can run in different environments with different interpreters. You can have, as we have seen, terminal interpreters, or we can have things like web application interpreter. But I know, all of you, that you are not still sold on generators, right? So let's try to do something. I'm gonna show you something. Okay. So I want to show you a demo. So this is an application. It's a very complex application. You have never seen one like this one, I think. You can do things. You can change them. You can move inside. And you can see here that I have basically a list of users. And when I reload the page, you will see that I have that quick loading stuff. And I also have things like, if I say that I am offline, I will see that, oops, too much. Sorry, I want to say if I have a slow 4G, yes. You can see that now the application is loading. Yeah, loading, you see that appeared. And so this is a very beautiful React demo, right? Well, except this is not React. This is Restar. Restar is the name that I choose for basically a full-blown UI library that is very similar to React, but it is fully built by using generators. And so, going back to, so behind the scene, Restar uses the same instruction system that we have seen before with the OP pattern, because behind the scene, Restar defines elements by yielding instructions. It yields an instruction to tell, please open an element with this type and these props, or please emit a text node, or please close the previous element. And they describe what to render, okay? Not the actual implementation of how to render. And then components are just generator that yields that instruction. A button, for example, yields the open element, and then yields a text node for the label, and then yields a close element to close the element. And again, this is just a generator that's yielding instruction. And these button components can also maybe be more generalized in an H function, and that will basically yield those three instructions for us, and will take also like children, exactly like in JSX. Now that you can see that invoking other components is just calling the function, and that's really it. So we have, for example, a to-do item component and a to-do list, and in order to create a to-do item, we just call the function, we spread it, and that's really it. So again, this is exactly the same yield star composition pattern that we have seen before, but is applied to our user interface. And turns out that I don't need the fragment component, because generators can yield as many values as they want. So I don't need a fragment component. I can just loop through my items and yield as many nodes I want. And also I get typed context. And let me maybe show you this through my code demo, because maybe that's better to see. Here, for example, I have a user fetcher component, and you can see that I create a context, and the context have a type that will be put into the type parameter just to say, hey, this component needs users, and this is the actual shape that will be given back. And then I can do things like, yeah, I want to read the API-based URL from the context, and then I will use a promise and get back the value, and then provide that through the context to our children. And we can see that indeed our application, for example, here we have a to-do item that reads the user context, so we can see that in type parameters we have users. And the same goes on for our app that needs both the users and the API-based URL. And error boundaries? No thanks. I can just use a try-catch, and that's really it. I don't need an error boundary component. Yeah, you know, JavaScript has try-catch instructions, so I can just try to render the component, and if an error happens, we can render something else. And we can also, our code in the system, I have coded that if the error is null, it means that the problem has not solved yet. So that's basically just our loading state. But again, how's that all implemented behind the scene? Behind the scene, it's all an actor system. We have basically a coordinator that's built on generator, and the coordinator is basically the component of the system that creates the component instance, and the component instance, as we have seen, will yield the instruction. And when it will yield an instruction, for example, an open element instruction, it will broadcast that instruction to other part of the system, like the reconciler, or the context manager, or the hooks manager. And then some other actors in the system may say, yeah, I know how to handle this instruction, please, I've handled it, this is the result, advance to the next instruction. And then the coordinator will say, okay, this is the next instruction, and so goes on. So it's basically a really complex system, but it's built with very simple parts, because every single actor have a very specific responsibility. For example, the reconciler actor is behind the scene very, very simple, because it basically differs the real DOM with the instruction it receives, and when it receives an open element instruction, it will see if the current DOM element have or not that child. If it's not there, it will create it, and then it will move the current position, the current state, into that just created element. So if we yield another open element instruction, it will be created as child of that. And when we receive a close element instruction, we will basically step back and go up into the tree. So basically, we are as we receive instruction, we will step into our DOM and basically ensure that is actually what we are rendering. And we can do also the same thing for other things like the context, because we have instruction that tells, okay, I am beginning to rendering everything, so I can clear my current context. I can have instruction that says, I want to read the context, and it will basically send back to the actor system the reply and to advance, and other instruction, for example, to update the current context. So yeah, that's quite a lot. So yeah, wrapping up, I am surprisingly on time. So wrapping up, what I want to tell you to keep in mind is that you already use some kind of generators every day, because behind the scene, you may be still maybe transpiling back to a generator if you target some old enough environment. So maybe we can embrace them and take advantage of the unique pattern and type safety they offer. And I'm sure that if you do that, you may end up building something so powerful that can change the way you code. So thank you very much for joining my presentation. Again, these are my social media. And again, if you want to talk about effect or whatever, I'll be there. So thank you again.